So in this video, we are going to play with type definition and type classes implementation. And in order to do so, I want to remember you that you can find all the code of this series searching for GitHub Michele Nuzzi / Plutus oriented Haskell. And in particular, the code for this video is in the exercises folder and then in the data types folder. So let's start by the first exercise. And in the first exercise, I do have already defined a data type called complex, which does have three constructors, RE for real, and IAM for imaginary, and a complex constructor. For the moment, we are going to work with doubles, which are types for number. We can see, in fact, that the double implementation does have an instance for the num. In any case, later in the video, we'll see how to generalize this definition and also what we are going to implement. In any case, back to the first exercise, I would like you to implement two functions, and those functions are called real and imaginary, which, given a complex number, return the real component in the case of the real function and the imaginary component in the case of the imaginary function. And just in case you didn't know, a complex number is made of a real component, which is a number identical to the one we are used to, and imaginary component, which is again another number identical to the one we are used to, but multiplied by the I imaginary unit. And we can identify a complex number by identifying the real part and the imaginary part of the number and summing those. Of course, if one of the number is 0, then we have only an imaginary number or only a real number. In any case, that is just how complex numbers are noted. And these functions are requesting in the previous notation to extract the A and to extract the B. And given these three constructors, we assume that the real constructor does create a complex number with no imaginary part. The imaginary constructor does create a complex number with no real part, and the complex is used to create a complex number with both a real and an imaginary part, where the first parameter is the real. So now you should be able to implement these two functions. So you can now stop the video and try to solve the exercise. All right, I assume you have paused the video and solved the exercise. So I'm going to show you my solution. And for this first exercise, the solution is just to use pattern matching to extract the argument given based on the constructor used for create a complex instance and then returning it. So the first exercise was quite simple. And if we try to go in GACI and load these definitions, we see that those work as intended. But if we try to print an instance of a complex number, we see that we get an interesting error. And by now we should be able to understand what this error is trying to telling us. And the error says there is no instance for complex of the show type class arising from the use of print. Well, print is the function used in order to, of course, print something in the console. And this error is telling us that we need a show instance for the complex data type in order to print it. So, well, we know how to implement instances of type classes, and we can ask for what is needed in order to have a show instance. And by going on the top, we see that the class show is defined like so, and the minimal in order to have a show instance is to define either a show prec function or a show. And well, actually, the easier and probably most used is the show function. So we are going to implement this, and we see that the type signature of show is a function that given an a, and an a is a particular instance of this type class, as we see here. So given something that is showable, returns a string. Cool. So we just need to get a string from a complex data type. And this is exactly what the next exercise is about. And we have to define here an instance for the show type class. And I'll leave here an example. Show complex 2 and 1 should evaluate to a string like this. Very similar to what we saw before, where the a plus bi is a complex number. The show function should return a string similar to this. So yeah, this is the second exercise, and you can now pause the video and try to solve this exercise yourself. Well, this exercise too shouldn't have been so difficult, but let's go to see the solution also here. And my solution is written in these 2 lines, and I do use the utility function we defined in the previous exercise, but notice how you could have implemented an equally valid solution also without using those functions. In any case, since double is also an instance of the show type class, and we can of course see this by asking for the infos of double, and we see that we do have right here an instance of show for double, so we can use the function show with a double instance. And so I define the show function that given a complex returns the string for of the real part of the complex concatenated with a string of a plus concatenated with the show of the imaginary part of the complex concatenated with the string of an I. And by loading this file, we can see that now we can just print out an instance of a complex number. For the third exercise, and here comes the fun, I would like you to implement an instance for num of the complex data type. And in the definition of num, we see that some functions are required in order to have an instance of num, but here I do have already defined some of them, and you have just to define these 3 functions, which are the addition, the multiplication, and the negate function, which is supposed to return the negative version of that complex number. And these operations are so defined. The addition of 2 complex numbers is equal to the sum of the real parts and the sum of the imaginary parts. And the multiplication is so defined. Given 2 complex numbers, this is just doing a by c, then a by d, then b by c, and then b by d. In any case, this is the formula of doing such an operation. And please remember that I multiplied by I, so the imaginary units multiplied by themselves, or also I squared, is equal by definition to -1. And with these informations, you should be able also to implement the multiplication between complexes, and then the negate function should not be that hard. The negation of a complex is just the negation of its parts, both real and imaginary. So please now pause the video and try to implement these 3 functions in order to have a num instance for the complex data type. Alright, I hope you were able to solve this exercise too. So I'm going to show you my solution, and here are the 3 functions I defined. So the plus is just constructing a new complex using the complex constructor in order to implement the formula that is written here. So this should not be that hard to understand how it's working. The negate function also wasn't that complex to implement. And here is the multiplication function. And here I'm doing a bit of pattern matching. Here, as a first case, I do have the case in which both numbers have been constructed with the imaginary constructor. So we know for sure that there is only an imaginary part, and this is done in order to prevent this case to do unexpected things. In any case, here I'm just returning the multiplication of the two numbers negated and then wrapping them inside a real constructor so that we have a complex instance. Of course, we could have the same definition also for the cases in which the complex constructor has 0 as a real part. In this case, also this constructor is just building a complex number which is only imaginary, and the implementation is the same. In any case, the general implementation is this one, in which, of course, I'm just implementing this formula right here, and we can, of course, test this implementation. And one cool thing of implementing an instance of the num type class for the complex is that we can now use these functions of the num type class with other instances of the num type class. As an example, the plain number 2, and we see that this expression works fine, but we can of course also use the I, and we see that that works too. In fact, we were working only with this number, and the I is doing what expected, is rotating by 90 degrees the complex number. And we can also try to see if the I definition works, and we see that this is correct. In fact, we return -1 only in the complex form. We can have maybe some more complex expressions, but still the result works. So we can assume that we did a good job. So as promised, now let's see how we can generalize this implementation, which for now only works with doubles. And in order to do so, we can parameterize the complex data type definition with an m parameter. And as defined here, this n could be anything, even strings, but there is not much that we can do about this. In fact, using type classes in data type definitions requires this extension, which, as we know, is deprecated. And usually when something is deprecated, we may want to avoid it, but still we can use type classes in the utility functions, in the instance implementations. So the real function and the imaginary have not really changed. The only thing that changed is the type definition. Well, of course, the type here that matters is this one. The only thing that changed is that we no longer return a double, but we can imagine this n to be a double, and the definition will be totally equal to the one previously implemented. In fact, here is just like having the n equal to a double, but using this definition, we can add constraint to the general n type, and we are saying that this n must have instances for the num type class and the show type class in order to work inside this function. The same is true for the imaginary, and we are doing something very similar inside an instance of another type class declaration. Well, in this particular declaration, the only constraint that we care of is that n must be showable. In fact, we were sure about this when using simple doubles, since of course we know by the double implementation that this is a valid type that can be used with the show function. But since here we are using a generic type, we have to put this constraint in order to be sure to use show with whatever is returned from this function. And that's also why we need this constraint here. And we use this identical constraint in the instance declaration for the num type class. And here the num constraint is useful, otherwise we couldn't have been able, as an example here, to use the plus between the numbers, since, as I said before, without this n could have been really anything. So if n is anything, we are not really sure that we can use the plus, and we can of course see this because if I now remove this constraint, we see that we get a lot of errors saying to us exactly what I said a moment ago. But yeah, this is what you need to do in order to generalize a bit this definition. We see that the only things that are changing are some constraints and some type definitions, but the actual implementations are still the same. And with this, we also saw a practical example of implementing a data type with some type classes. So if this video was useful to you, consider to subscribe to the channel. If you want to support the creation of this content, in the description below you'll find a link that allows you to delegate your data to the Harmonic pool and earn interest on top of supporting the creation of this content. In any case, I want to thank you for your time. Remember to stay decentralized, and I will see you in another video. Bye bye.